Okay. Hello, everybody, and welcome again to our second Hubble Hangout of the day at the 225th meeting of the American Astronomical Society. We're live, folks. This is it. We are in our exhibit booth, and Carol's with me, and as well as Zolt LeVay, and soon we'll be joined by, this empty chair will be taken up by Paul Scowen, who actually helped take the image that we're going to talk about today, because as you may not know, and if you don't know, you know now, that Hubble, we are celebrating the 25th anniversary of the Hubble Space Telescope being in orbit above our heads, and that is remarkable, folks. No other telescope has been up there that long, I think. That's right? Okay, so this is the time we're getting started. It'll all culminate in April, on April 20th, and to celebrate this auspicious event, this auspicious occasion, we have released, the Space Telescope Science Institute has released an anniversary image, but it's not the anniversary image, right? It's
one of the anniversary images, a kickoff of festivities.
That's right. Now, we are in a bit of an awkward situation, folks. I am doing this live, and ordinarily we have Hangouts on air, which give us this ability to share our screens. But because I'm streaming via a backpack that does not allow me to use the internet from the convention, I'm kind of limited by what I can do technologically.
Streaming camping.
Yeah, we're streaming camping, but we have bandwidth where no one else does, so that's cool too. So we are streaming straight to YouTube, which means that I don't have the tools ordinarily available to me to share my screen and to show you the image, so it's kind of awkward.
We also have hecklers all around us, our colleagues.
That's right. So while we're broadcasting, people want to make faces at us. So what I've done is I've taken the 25th, the image was just released at 2:15 Pacific time, so it's brand new. It's just been put out. I put a link to the press release on the Google Plus event page, so you can go and look at all the different versions of the image there, as well as on the Google Plus page, our Facebook page, and it's on Twitter. And if you need somewhere else to go see it, I would encourage you to let me know, because I've got Ishan Prescott here from NASA monitoring the YouTube. But don't unveil it yet.
Oh, sorry.
Our super high tech.
I can't show it to you.
Our super high tech way of doing it here.
This is why it's camping.
So with that, I'm gonna hand this over to. He's monitoring.
Show one part of the image.
In a minute, I'm gonna tell them how they can interact with us. Google Plus event page, YouTube comments, Twitter, Hubble Hangout hashtag, and Hubble 25. Okay, we're also looking at that one, and we will get to your comments and questions. We hope you have some. Okay, Carol, go ahead.
Okay, so this is the first part of the M16 image release, and it's the optical part of the image.
Okay, now get ready. This is weird. This is going to be weird. Reflections and all, that's right. Okay, so what you're looking at is, what are they looking at there? Zolt, tell us a little bit about what we've taken and why.
Online, of course, at hubblesite.org, so have a look.
So what we're looking at is the famous, what's become known as the Pillars of Creation, M16, the Eagle Nebula, whatever you want to call it. These are pillars of gas and dust that are being eroded by stars that are off the picture. So we've taken a new image with the Hubble Space Telescope with the current instrumentation on the telescope, the Wide Field Camera 3 with C3 instrument. So this image that you just saw is a visible light image in the light of three chemical elements: hydrogen, oxygen, and sulfur. The colors have been assigned to the black and white images of those three images, so in the sense of the oxygen is blue, hydrogen is green, and the sulfur is red. And when you combine those, you get this nice, colorful image. We actually made a second image in infrared light.
And tell them when that first image came out.
Okay, so the original image that this kind of reprises was made in 1995 with the WIFPIC 2 camera on the telescope back then, and became this iconic, very popular image.
A lot of posters.
And so we thought we'd see what
Pillars of creation.
the pillars of creation. And it's pillars of creation because stars are being created inside these pillars. And pillars because this is relatively dense gas or actually there's a dense material at the top, and the less dense material is being eroded away and being shadowed. Actually, the pillars are shadowed by this denser material at the top, and so it's creating these pillars. So that's why it's pillars of creation.
So this camera, the WIFPIC 2 you're talking about, had lower resolution, and the field of view at the time was a lot smaller and narrower. And like Carol said, this is in the optical wavelengths. Now, as you all know, back in 2009, we sent the space shuttle up there, and John Grunsfeld gave us a new Hubble. He basically rebuilt the thing, put in new cameras, new filters, new electronics, new gyros, all kinds of things. So Hubble is now virtually a brand new telescope since 2009, and and the main camera being used now is an infrared camera called Wide Field Camera 3, and so we took the picture again. And this time, they saw what?
We saw this. Well, it's still coming up on my screen. But the infrared version of the image, which is... Oh, there it is. Finally came up. So the most obvious thing about this image is that the pillars more or less disappear. And what's happening is that the infrared light is able to pass through the material. The material hasn't gone away, but the light is able to pass through more of that material, and we're seeing a lot of the stars that are embedded in that nebulosity or behind it, which we can't see in the visible light because that material is absorbing all that visible light, but the infrared light is getting through. So it's really a very, very different picture than what you see in visible.
And the field of view is a lot wider too, correct?
The field of view of both the visible light camera on WIFC 3 and the infrared camera on WIFC 3 are wider than the WIFPIC 2. The field of view of the WIFC 3 visible light camera is larger than the infrared. And we also made a little mosaic. So this is not just one pointing of the telescope, it's actually 4 pointings of the telescope in a 2x2 grid. So we made a much wider field of view, and we really wanted to see the area around it. One of the most important things to do was to get the bottom parts of the pillars, and it's interesting, one of the interesting features about the image is how the pillars kind of actually disappear at the bottom, and they're kind of disconnected from the rest of the nebulosity that there's more of down underneath.
Well, I'm hoping I will get our astronomer here to tell us a little bit more about the details of what's going on astronomically in there. But Carol, do you have any comments? What strikes you about this image?
Well, one of the big questions when the first image was taken, besides the fact that it really demonstrated how powerful Hubble Space Telescope was at the time and what its bright future was going to be, is what's inside those pillars. And so now that we've seen the infrared image from Hubble at a similar resolution to the optical image, we can see that the very top and the dense regions, there are indeed, it was suspected, and a couple of stars were seen, but it was suspected that there were stars forming in there. Now, I know at one time there was some speculation that there were lots of stars forming in there, and I think the scientists who originally worked on the first image have now been looking at this image, and they haven't had it very long, but my understanding is that what they said is there are fewer stars than what they thought. And part of the reason is that the top of the pillars is so dense, and that's why even in the infrared you can't see through them, so that it's difficult for many stars to form in there. And also the other interesting thing is that the brightest stars are actually ablating and blowing away some of that gas and dust. And what I found interesting is that from the top to the bottom of the pillar, it takes it's 5 light years, so it takes 5 years for the light from the top of the pillar where the really bright stars are to reach the bottom. So that stuff is sort of dissipating, but very slowly.
So I have a question for either one of you. Is there been anything different about the nebula since the first one was taken? You want to comment on that?
That's one of the things we wanted to look at right away. With a almost 20-year baseline of time, you'd kind of expect in this very dynamic environment that you might be able to see some differences. Now, the opposite side of that is that it's a very large structure. So you'd have to have things moving incredibly fast to have them move enough, and it's far away.
Yeah, it's far
So
away,
you'd have to have it moving very fast to be able to notice, even with Hubble's incredible resolution, that something moved. And in fact, when we started to look very closely, we did actually see one little place where we did see a little bit of change, whether that's a motion or just a change in that structure. We're not entirely sure, but it looks like what's happening is there's a jet from a very new star near the top of one of the pillars, and we noticed that the very end of that jet structure is a little farther away than it was in 1995. So, and it looks pretty clear, and it looks convincing. So we're kind of pretty convinced that we're actually seeing some motion. There's some other little structures around that we see, not very many, but some structures around that we see that are different from the 1995 image.
I'll tell you what strikes me about astronomy today is just how much that is possible now. There was a time when the telescopes were so resolution, and there was just no ability to resolve much of any detail, we all thought the universe never changed, that it all stayed the same. And now we have telescopes and detectors that are so finely tuned and such a high resolution that we can actually gain these insights over 20-something years.
Plus the longevity of the telescope. That's a great thing about how long it's been able to last, and it's been improved and serviced, so it's lasted this 25 years. And that's a fairly large baseline, maybe not in cosmic terms, but certainly in human terms and astronomical terms, it's a relatively long baseline of time, and then you can start to see these kinds of differences.
Another interesting thing that was noticed in the very first image, I guess we have a comparison now.
We're going to creep up on the camera.
Yeah, we're going to creep up on the camera. So what was noticed in the first image, the iconic WPIC 2 image, is that the pillars seem to have very sharp, well-defined edges. And now that we have twice the resolution, it turns out the pillars have very well-defined sharp edges. So that impression, even sharper, and in fact they're only something like 100 astronomical units, so that's just a little bit bigger than the size of our solar system thick. So they're not fuzzy edge, they're very, very sharp edges, which is really very curious, because usually whenever we look at these star formation regions, we see that the regions are very diffuse and sort of surreal. We see that surrounding the pillars, but the pillars themselves have very sharp edges, and so that was another important result in looking in both the infrared and the optical to determine whether our first impression 25 years ago was really true.
So is there any, are there any surprises that came out of this, things that we didn't expect to see, or was it pretty much everything except for this one jet that we saw that was an interesting motion? Was there any surprises, things that jumped out at with the new image?
I don't think there was a lot of surprises. I think what Paul Scowen, who worked on the original data, did point out these very sharp edges of these ionization regions that was somewhat surprising, that it's even sharper than they thought from the original. And they were surprised at how sharp they were in the WPIC 2 data. But now they're seeing that they're even sharper. And that means, what that means is that there's a very small region of space where this ionization has an effect, where it changes over a relatively small span of space. And that space is even smaller than they originally thought. So it's things like that. Although, part of the reason we did the observation was to come out to have a picture to look at, and we kind of knew what to expect because it hasn't changed much since 1995, and the instrumentation, while it's improved it's improved greatly in resolution and sensitivity and so forth, it's really the same kind of camera, and we use the same filters and intentionally so that we could compare kind of apples and apples, the images, the 1995 image to the 2014 image. So that was all very intentional.
Oh, okay, Paul's here now. So we have Paul Scowen with us. He's the you just got back from a press release. Welcome to our. We're on.
How's it going? Yes, an awful lot of questions and stuff, but that's okay.
So why don't you give us? So what we're talking about. We were talking about the image itself. Joel was telling us some of the ways, some of the wavelengths and the differences, things that they found that varied from the 1995 image.
Yes.
So what are some of the things scientifically that you found interesting about this image?
The neat stuff about these new pictures is you've got several things going for you. It's about three things that are really are so much better than the data that we took. Remember, the first data we took was with the first camera, right? The first clear camera, and it provided at that time the sharpest field of view, the sharpest view of what the structure in the nebula was like. With these data, we've got twice the resolution. Okay. Now, and that's spectacular because a lot of the physics that we learned back then was understanding how the photons coming from the massive stars at the center of the cluster were actually ablating the walls of the nebula and eroding it away. When you look at the tops of the pillars, you can see these blue streamers, right? What you're looking at there is the ionized gas from those massive stars being ablated by high. There we go. It's a little seat of the pants, this, isn't it? Okay. So the streamers at the top there really show you. We already had some suspicions that this went on in the walls of H2 regions, but this was the first real photographic evidence of it, that you were looking at gas being eroded away from the walls of the cavity. And that's great but you really had to model it. You had to understand how sharp the edge of those pillars was. And so when you look in the picture that we took in '95 and you compare it to any ground-based picture that's been taken before that or since, for the most part, you can tell it's sharp, but you didn't know how sharp it was. And so Hubble offered that for the first time. Now with these data, we look at, and we can see it's even sharper than we thought.
So yeah, Zolt mentioned something about that. What's the big deal about that? What's the big deal about the sharpness?
Okay, the sharpness is when you're trying to do the modeling. Okay, you do the classical numerical modeling of the gas dynamics of the interface. One of the things you have to build into that is what kind of density contrast are you running up against. When you're building your model, you need to know how sharp a wall it is.
Density contrast.
Yeah. So like. So in the center of the nebula, it's really tenuous gas. Okay, the reason you see the pillars the way they are is that it's much denser gas. Okay, it's like running up against a really sharp fog bank here on the Earth. All right, but instead, where I'm from in Arizona, we don't have fog banks. We have dust storms. And believe me, when you run into one of those, you know that's a pretty sharp contrast.
So that's a sharp edge.
That's a sharp edge. And understanding how sharp that edge is affects the way you model how the photons, how the light, how the ionizing radiation from those central stars makes it through that wall. And the reason we care is why the infrared picture is important. What is the difference? When you look at the two pictures, right, what's the big difference?
It's still pretty dark in there.
It's still pretty dark, but there's so many stars, right? The reason you see so many stars is you're seeing through that interface, through that dust storm edge, if you like. And the reason is because as that interface gets ablated away, it compresses the gas behind it. That region is called the photodissociation region.
Oh yeah, sure.
Okay, yeah, which to most people are like, yeah, okay.
I was going to say that.
But what the impact of that is the gas gets compressed and you make a second generation of stars back there. Oh. All right.
So and the compression as from the first generation makes a second
yes.
generation.
So the fact that you made stars in one part of the galaxy, in that particular part of the neighborhood, intimately affects how the second generation of stars around it forms. Now, the thing that the Eagle Nebula picture in 1995 represented was that because when you look at the top of the left-hand pillar, you see all these little dragon heads sticking out of the top. Those are protostellar systems caught in the act of still collapsing, still accreting gas to get bigger and brighter, and they're being dug up too early, right? They're being dug up and thrown out into that by the other stars being formed and ablating their nursery interface or environment. And so that was the first time we saw direct evidence that primary star formation affects how big or how pervasive or how bright the second generation of stars can be.
And so that's a pretty wild place in there then. A lot of stuff's going on.
Oh, yeah. Just about any of these H2 regions really are very dynamic environments.
So I have a question that I wanted to ask you before. And I'm not sure if anybody asked you, but in some of these places, after the original observation, and we did pillars of creation and star formation, we started looking at Orion and some other places, and we started talking about the formation of exoplanet systems.
Yes.
The little fingers that your dragon heads that you're talking about, are those places then going to be disrupted and not able to form exoplanetary systems, and maybe other places in the pillar will, or do you have a feeling for that? Or
great question, because she's a great straight man, because the whole point of the infrared image is that in places the pillars look absolutely translucent, right? But still in the upper segments of each of those pillars, they're still pretty dark in the infrared image. But what you can see when you blink the two pictures together is that there are stellar sources buried in there. And so we can do exactly the assessment you just described. That, when we originally did the analysis 20 years ago, I think we identified 60 to 70 possible protostellar clumps, right? But the number of objects that we had a stellar source in the heart of, we couldn't assess in the optical because it was completely shrouded, right? But now in the infrared, that veil has been lifted, and based on just my first analysis of the data, it looks like 10 to 15% of those clumps do now have stellar sources in the center of them. So that gives you an immediate assessment of how many of those clumps ultimately will amount to nothing, and how many of those clumps ultimately will become a star, but probably a lot smaller star than it would have been because of the process. Yeah. Now, your other part of your question is about the planetary systems around them. Right. Because the question is, when you ablate those things, when you start beating them up with these massive stellar winds, are you actually cutting off the sink of material that might ultimately end up in a circumstellar disk, and that might ultimately become that star's version of a solar system? There's been actually a number of people who have done a lot of numerical modeling work of this kind in the intervening 20 years, because of all the other nebulae. Right, we've seen this kind of stuff going on in Orion, we've seen it going on in the Trifid, we've seen it going on a variety of different places. So the question is that they were trying to answer was, if you have a bunch of protostellar and protoplanetary systems like that in the close proximity to massive stars, what are the chances? How long can it actually stick around? And the remarkable thing is that it depends on where they are in the phase of aggregating material, but a lot of them actually can survive. And where some of this became actually really quite at home and personal was my own home department at Arizona State. We have a lot of different folks working together. We've got geologists, meteoriticists, planetary scientists, all kind of stuff working together with astronomers. We have one of the best meteorite collections in the world, and we went in and had a look at some of the meteorite evidence for abundances of different kinds of isotopic materials in the meteorite matrices that we see from objects that have fallen to Earth here. And when you look at the isotopic abundances of things like iron and nickel, you find that they have been enhanced in exactly the way you would expect by a supernova going off really nearby, right, when our solar system was in exactly the phase. Right, because statistically that's what it tells you, right? For your solar system, our solar system, to be caught at that very instant of forming, and a supernova just happens to be right next door and go boom, means that we formed in a massive stellar environment just like the Eagle. So when we're looking at the Eagle, we're looking at old family photos, right? That's really what, exactly.
So the supernova you're talking about, though, that isn't necessarily in the Eagle Nebula itself. It's just somewhere in the vicinity, right?
No, the very massive stars at the center of the nebula, right? The ones that are lighting up the whole neighborhood. The only stars that can kick out that much ultraviolet radiation are the most massive stars, are the OB stars that we see that are 10s, 20s of solar masses in mass. And those stars are the college frat brothers of stars in that they live fast and die young, and they don't last very long. They only last a few million years, and then they go foom.
Okay.
And so it becomes a statistical argument, right?
Yep. So the first generation of stars, do you have a sense how many of those there are in the region?
When you look at any given region of star formation, there is this universal quality control curve, which we call the initial mass function.
Oh, okay.
All right. So when you make a certain number of massive stars, you make a truckload of solar mass. Yes, right. You make an awful lot of low mass stars for very few massive ones, right? And it's just a sliding vertical scale. So for you to have any massive stars at all in this neighborhood, you have to have made a bunch of low mass ones. And one of the guys in the press conference asked me that question because we can now see through the back wall of the cavity and we can see so many stars in this picture. Is it commensurate? Is it in fact does it make sense concerning how big we think the cluster is? And the short answer I've got right now is I don't know, because I haven't had a chance to count them all. All right, but because of the colors, because the infrared picture was taken in 2 bands, you can figure out how massive each of those stars is.
That's amazing.
So
I want to get back to the point you were making about we were born in the same kind of neighborhood as the one you're talking about now. What other stars that are around us would have been a part of that, do you think?
Well, the problem when you make a cluster of stars is they all form in the same place.
Right.
They form in the same cavity, and when you look at the Eagle, you're looking at them just busting out, right? They're all teenagers going out for their first party and stuff, right? They're all coming out of their nursery and being exposed to the interstellar environment. The problem is dynamically, they're not just sitting there. They're moving, they have their own proper motions, and the cluster over time starts to dissipate. It enlarges, stars go in different directions. Some have higher velocities than others. And the other problem is they have a finite width, and within a spiral galaxy, you have a gradient in rotational velocity that causes shear. At any given radius, our galaxy, any spiral galaxy, the part of the neighborhood there that is closer to the center of the galaxy is going to rotate around the center of the galaxy quicker than the stuff that's maybe a little bit further away.
So, if we were the cluster, this is our intro astronomy. If we were the cluster and the galactic center was over there, Zolt would be moving the fastest, and then me next, and then you guys would just drift away.
Right. And what that means is that the cluster, as we understand it, as being this beautiful round cluster of stars, gets stretched out and smeared, and so stars that form together end up
all over the place,
spatially streamed out along that radial.
But you said also they each have their own proper motions too. What causes that? Just getting bumped around by other forces in the nebula?
It's just randomness in the way the collapse happens. When you take the cold, dark material in a molecular cloud and you collapse it, there's always some rotation built into it. And so there's always an angular momentum vector or a preferred axis around which it spins. And they're all different. All the stars have different rotation vectors, and as they collapse, the mechanism by which that material makes it onto the surface requires material to be ejected along the rotation axis. That's why when you see new stellar systems like this, they always have this characteristic jet sticking out of them. And in fact, in the data, in one of the pictures we've got there, over that 20-year lifespan, we can see one of the jets moving, right? Right. And so that's telling you that's an immediate signpost that says, look, we just made a star right here. Because you can see the jet of material being spat out of it as it tries to aggregate material down into the star and into the protoplanetary disk that ultimately becomes the solar system. as you can see in front of the camera right now.
Yes. Thank you, Zolt, with our high-tech wizardry here. So Zolt said something about the pillar, or no, it was Carol that said something about the pillars being 5 light years or so.
Yeah, about 5 light years long. Yeah.
How big would you say the whole region in say area?
The cluster itself, if you look at a typical ground-based picture, the pillars themselves are really quite small compared to the rest of the cavity. So if that's, if the pillar length is 5, I would say the cluster has to be a good 40 or 50 light years across.
And I predict a lot of planets coming out of this one too. I don't know. Seems to me like there'll be a lot of them coming out of there. So Zolt, let's get back to the image itself. Can you give us some idea of how many orbits, things like that, maybe went into it? Some images like that. Do you have any rough idea? No, okay. If you don't know it off the top of your head, I'd just like to give people a sense of how long it took to put together.
It's probably 15 to 20, isn't it?
Well, it was let's see, 4 pointings, 3 filters per pointing in UViz, 2 filters per pointing in infrared, and I believe we were able to fit both infrared pointing filters in one orbit. So that was like 4 orbits or less for the infrared, and 3 times 4 is 12 orbits for the UViz. So, 15 orbits or so. I believe we had 15 orbits for this. So,
and each orbit is an hour and a half, right?
Fully an hour and a half, but you only have 40 to 50 minutes within the orbit to actually. No, unfortunately not in the continuous viewing zone, so there's all kinds of overheads with switching filters and switching pointings, so but it worked out okay. I mean, we had enough time to get a decent images.
A point that needs to be made concerning the original data is that in that those were very comparable exposure times to what we did 20 years ago, but we get 10 times deeper, right? Well, which is very cool. And what that illustrates, you've got the infrared channel, you've got twice the resolution, and you're going deeper in the same exposure time. What that illustrates is how much better Hubble became as a facility in the 25 years.
Yep, we touched on that at the beginning. Yeah, it's like the advantage we have of Hubble being not only close to Earth orbit, but also the fact that it was designed with the space shuttle in mind to repair it, has really made Hubble one of the most amazing, longest-lived instruments we've ever had. Right. So let me turn to Ishan and see if he's found anything. Nothing on the social media things? Okay. All right. Well, you guys have any final comments on anything you want to mention that we haven't covered here?
I think there's still an awful lot of science to pull out of those data. And I've already told Zolt I want to write a paper on this because we have the ability to go in there, look at those stellar populations, look at how much sharper that interface is, redo the calculations about the gas dynamics in the nebula, and really understand what the stellar formation environment in this nebula looks like. And these new data really gives us that chance.
Oh, it sounds exciting. Thank you, Paul. I appreciate your time for coming by. Congratulations on a great release. This was awesome. Oh.
I'm trying to load the image of the entire region. And so if you look up M16 astronomy, if you look up M16, you'll get the M16 rifle. But if you want to know about M16 astronomy, or nebula, M16 nebula, look up. There are some images of the entire region, which I actually got the image to load, so I'll show you right now.
Okay. So, okay.
So yeah, we're looking at the wider view of the whole Eagle Nebula. So you can see that the pillars were looking at a really very small part of that entire complex region. And there's other pillars in there. There's another pillar that we took Hubble images of a number of years ago with the ACS camera, and comparable structures, very interesting structures. And I just wanted to kind of say that one of the reasons we took this image was to kind of bookend the project of the Hubble mission. So it's almost 25 years it's been in operation. That's, as Paul said, I think that's an eternity for a space mission, really, because many space missions only last months to years, and Hubble's been, because of the ability to service it, it's been not only operating for this amount of time, but has been improved, and it's much better than it was when it first started. and it's stayed competitive with the rest of astronomy. It's been still in the forefront of astronomy, even though it's 25 years old, which is old even for a ground-based telescope, really. So that's one of the primary reasons we did this image, and we want to highlight the history of the mission, and we thought it'd be a good way to do that.
Right, so I want to thank all you guys for joining us. It's been a lot of fun. Thanks for joining us, Paul. This was really great.
No worries.
Yeah, it's a lot of fun.
Thanks. Congratulations on the
Yeah,
press release.
congratulations.
Look it all up on the Hubble site.
Yes, I've got the link on
All
the.
the images and the movies and all that stuff.
Right, we got a lot of stuff for you to download, so we hope you'll do that. And Carol, I hope you'll join us. Our next hangout will be at 4:30 Pacific time, where Carol and I will do a recap of the AAS meeting today. Some of the things that we found interesting for about 15 or 20 minutes. We'll sit and chat about the end of the day, and so we hope you'll join that. I want to thank you all for watching, and as always, keep looking up. Okay. Hello, everybody, and welcome again to our second Hubble Hangout of the day at the 225th meeting of the American Astronomical Society. We're live, folks. This is it. We are in our exhibit booth, and Carol's with me, and as well as Zolt LeVay, and soon we'll be joined by, this empty chair will be taken up by Paul Scowen, who actually helped take the image that we're going to talk about today, because as you may not know, and if you don't know, you know now, that Hubble, we are celebrating the 25th anniversary of the Hubble Space Telescope being in orbit above our heads, and that is remarkable, folks. No other telescope has been up there that long, I think. That's right? Okay, so this is the time we're getting started. It'll all culminate in April, on April 20th, and to celebrate this auspicious event, this auspicious occasion, we have released, the Space Telescope Science Institute has released an anniversary image, but it's not the anniversary image, right? It's
one of the anniversary images, a kickoff of festivities.
That's right. Now, we are in a bit of an awkward situation, folks. I am doing this live, and ordinarily we have Hangouts on air, which give us this ability to share our screens. But because I'm streaming via a backpack that does not allow me to use the internet from the convention, I'm kind of limited by what I can do technologically.
Streaming camping.
Yeah, we're streaming camping, but we have bandwidth where no one else does, so that's cool too. So we are streaming straight to YouTube, which means that I don't have the tools ordinarily available to me to share my screen and to show you the image, so it's kind of awkward.
We also have hecklers all around us, our colleagues.
That's right. So while we're broadcasting, people want to make faces at us. So what I've done is I've taken the 25th, the image was just released at 2:15 Pacific time, so it's brand new. It's just been put out. I put a link to the press release on the Google Plus event page, so you can go and look at all the different versions of the image there, as well as on the Google Plus page, our Facebook page, and why.
Online, of course, at hubblesite.org, so have a look.
So what we're looking at is the famous, what's become known as the Pillars of Creation, M16, the Eagle Nebula, whatever you want to call it. These are pillars of gas and dust that are being eroded by stars that are off the picture. So we've taken a new image with the Hubble Space Telescope with the current instrumentation on the telescope, the Wide Field Camera 3 with C3 instrument. So this image that you just saw is a visible light image in the light of three chemical elements: hydrogen, oxygen, and sulfur. The colors have been assigned to the black and white images of those three images, so in the sense of the oxygen is blue, hydrogen is green, and the sulfur is red. And when you combine those, you get this nice, colorful image. We actually made a second image in infrared light. And
it's on Twitter, and if you need somewhere else to go see it, I would encourage you to let me know, because I've got Ishan Prescott here from NASA monitoring the YouTube. But don't unveil it yet.
Oh, sorry.
Our super high tech.
I can't show it to you.
Our super high tech way of doing it here.
This is why it's camping.
So with that, I'm gonna hand this over to. He's monitoring.
Show one part of the image.
In a minute, I'm going to tell them how they can interact with us. Google Plus event page, YouTube comments, Twitter, Hubble Hangout, hashtag, and Hubble 25. Okay, we're also looking at that one, and we will get to your comments and questions. We hope you have some. Okay, Carol, go ahead.
Okay, so this is the first part of the M16 image release, and it's the optical part of the image.
Okay, now get ready. This is weird. This is going to be weird. Reflections and all. That's right. Okay, so what you're looking at is, what are they looking at there, Zolt? Tell us a little bit about what we've taken.
Okay. Okay, so the original image that this kind of reprises was made in 1995 with the WIFPIC 2 camera on the telescope back then, and became this iconic, very popular image.
A lot of posters.
And so we thought we'd see what
Pillars of creation.
the pillars of creation. And it's pillars of creation because stars are being created inside these pillars. And pillars because this is relatively dense gas or actually there's a dense material at the top, and the less dense material is being eroded away and being shadowed. Actually, the pillars are shadowed by this denser material at the top, and so it's creating these pillars. So that's why it's pillars of creation.
So this camera, the WIFPIC 2 you're talking about, had lower resolution, and the field of view at the time was a lot smaller and narrower. And Carol said this is in the optical wavelengths. Now, as you all know, back in 2009, we sent the space shuttle up there, and John Grunsfeld gave us a new Hubble.